Okay, good morning students. Today I am going to explain some more problems related to increasing and decreasing functions. So in previous class we discussed certain problems, objective problems related to this topic, and today I am going to complete this topic, objective part of this topic. Let us consider this problem. Fx equal to sin inverse x whole square plus cos inverse x whole square is stationary yet. The given options are x equal to 1 by root 2 and x equal to pi by 4. Third one, x equal to 1, and fourth option is x equal to 0. Fx equal to sin inverse x whole square plus cos inverse x whole square is stationary at x equal to. Coming to the solution here, Fx is here sin inverse x whole square plus cos inverse x whole square. So consider f dash x, the first derivative. To discuss the monotonic nature of the function, consider the first derivative. Differentiating both sides with respect to x, f dash x is derivative of sin inverse x whole square is 2 sin inverse x into derivative of sin inverse x plus derivative of cos inverse x whole square is 2 cos inverse x into derivative of cos inverse x. So this is 2 sin inverse x into derivative of sin inverse x. Derivative of sin inverse x is by the known formula. This is 1 by under root 1 minus x square plus 2 cos inverse x into derivative of cos inverse x is minus 1 by root over 1 minus x square. Hence this is 1 by root over 1 minus x square into 2 by root over 1 minus x square into sin inverse x minus cos inverse x. Now the function is stationary. Stationary in the sense neither increasing nor decreasing. Now f is stationary. F is stationary means f dash x equal to 0. The function is stationary whenever it is neither increasing nor decreasing, hence the first derivative is 0. So this is possible for sin inverse x minus cos inverse x is 0. Once this numerator is 0, this f dash x is 0. So therefore, the function is stationary whenever sin inverse x equal to cos inverse x. The function is stationary whenever sin inverse x equal to cos inverse x. But sin inverse x equal to cos inverse x is possible for x equal to 1 by root 2. At 1 by root 2, sin takes the value pi by, sin inverse takes the value pi by 4. Cos inverse also takes the value pi by 4. Hence, at x equal to 1 by root 2, the function is stationary. Therefore, we can conclude that at x equal to 1 by root 2, f is stationary. F is stationary. Next. Next one. Next problem. The stationary point. The stationary point of fx equal to e power x plus e power minus x is. The stationary point of fx equal to e power x plus e power minus x is. Now to get the stationary point of the given function, let us consider f dash x. So differentiating both sides with respect to x, f dash x is derivative of e power x plus derivative of e power minus x. But derivative of exponential function e power x is e power x. Derivative of e power minus x is minus e power minus x. Hence f dash x is here e power x minus e power minus x. Now the function is stationary. F is stationary. F is stationary. F is stationary when f dash x is 0. Therefore, e power x minus e power minus x is 0. Therefore, e power x equal to e power minus x. E power x equal to e power minus x implies e power x equal to 1 by e power x, which gives us e power x into e power x is e power 2x equal to 1. Taking cross multiplication, e power x into e power x whole square, which is nothing but e power 2x equal to 1, which is possible for x equal to 0 only, since e power 0 is 1. So the stationary point is, the function is stationary at x equal to 0. So stationary value, write at first the stationary value here. Stationary value is obtained for x equal to 0, that means f of 0. F of 0 is e power 0 plus e power 0, that is clearly 1 plus 1, that is 2. That is the stationary value. So the function is stationary particularly at x equal to 0, and the stationary value of the function is 2. Hence, stationary point is x coordinate is 0. For x coordinate is 0, correspondingly the functional value is 2, that is the y coordinate. Hence the stationary point on the curve e power x plus e power minus x is 0, 2. This is stationary point on the curve. This is stationary value f of 0. The function is stationary at x equal to 0. So try to understand the difference between these two values. He may ask stationary value, or he may ask stationary point, or he may ask where the function is stationary. There is a little bit difference between these three. Next one. Next problem. The critical point of fx equal to modulus of 2x plus 7 is at x equal to dash. The critical point of the function is at what value of x? Critical point means where f dash x equal to 0 or f dash x does not exist. Critical point means the point where the first derivative is 0 or the first derivative does not exist. Critical point is a little bit different from stationary point. Stationary point means only f dash x equal to 0 follows. So critical point means where the first derivative exists and it may equal to 0 or the first derivative may not exist at that point. That is said to be critical point. Critical point means the point on the curve where f dash x equal to 0 or f dash x does not exist. Clearly, whenever you draw the graph of the curve, so from graph of the curve, the graph of the function is as if fx equal to mod x itself. The graph of the mod x is in V shape. Already we know that the graph of the fx equal to mod x is in V shape and completely above the x-axis, and it has a corner at x equal to 0. That means where this x is 0. So based on this graph, you can draw the graph of the curve fx equal to mod 2x plus 7 as like this. It has corner at x equal to minus 7 by 2, because at x equal to minus 7 by 2 it is 0. So it takes its turn at that point. It has a conical corner at x equal to minus 7 by 2. That means once the graph is edge on, once the graph is slided towards negative axis, the obtained graph is as equivalent to that graph. Instead of x, here we have 2x plus 7. Once 2x plus 7 is 0, x equal to minus 7 by 2. Hence the origin is shifted to minus 7 by 2. In such case, the graph is in this shape. Moreover, for x equal to 0, x is 7. This is 7, 0 comma 7. So the graph is in such a way. The graph takes its turn at x equal to minus 7 by 2. Generally, once the graph takes its turn or it has a conical shape, at that point the function is not derivable. The function is not derivable. Therefore, from the graph of the curve, here f is not differentiable or derivable. Within the bracket or derivable. It has no derivative because the right derivative and left derivative differs here. F is not differentiable at x equal to minus 7 by 2. Hence f dash x does not exist. Therefore, f dash of minus 7 by 2 does not exist. Therefore, The critical point is x equal to minus 7 by 2. So through graph of the given function, immediately we can find the given function is not differentiable at that particular point, since the graph takes its turn at that point. Moreover, the graph is in conical shape, a sharp corner at that point. Hence, the function is not differentiable at sharp corners of the graph. So here at x equal to minus 7 by 2, f dash does not exist. Hence, the critical point is x equal to minus 7 by 2. From this definition of the critical point may be a stationary point or may not be a stationary point in this case. Stationary point means f dash x equal to 0 only, it is stationary. So, the stationary point is certainly a critical point, but every critical point need not be stationary point. That is worth note point here. Every critical point is stationary point, but every critical point need not be a stationary point, but every stationary point is certainly a critical point. Similarly, next, the value of x at which fx equal to cos x is stationary or given by the values of x at which fx equal to cos x is stationary or given by. The given options are n pi for all n that belongs to z. Set of integers, capital Z stands for set of integers. 2n plus 1 pi by 2 for all n that belongs to z. Set of all odd multiples of pi by 2. N pi by 4 for all n that belongs to z. Multiples of pi by 4. And n pi by 2 multiples of pi by 2. So the values of x at which the cos function cos x fx equal to cos x is stationary. So for this let us consider the function and its derivative. Differentiating both sides, f dash x is d by dx of cos x. Here derivative of cos x is minus sin x. It is clear that derivative of cos x is minus sin x. To get the stationary values, taking f dash x equal to 0 implies minus sin x equal to 0. So sin x equal to 0. Therefore, x is a multiple of pi. A multiple of pi. Because sin 0 0, sin pi 0, sin 2 pi 0, sin 3 pi 0. So x takes the value n pi for all n that belongs to z. The sine graph is like this. The graph of the sine function is like this. At 0 0, at pi by 2 it takes maximum value 1. So at pi it is 0. So pi, 2 pi, 3 pi. At these values it becomes 0. So it takes maximum value and then comes to 0. and then it comes to minus 1 minimum value and 0, and then it takes maximum value and 0, like this. So this is the graph of the sine function, which intersects the x-axis at 0, pi, 2 pi, 3 pi. So these are all given by n pi, x equal to n pi. So sin x equal to 0 for all its values of x, which are multiples of pi. Hence, first option is the right option, where the function is stationary. This is the graph of sin x. Graph of sin x, y equal to sin x, or fx equal to sin x graph. F dash graph. This is the graph of f dash, not fx. Interesting problem. Let hx equal to fx minus fx whole square plus fx whole cube. For every real number x. For every real number x. Then here the options are h is increasing whenever f is increasing. The second option is h is increasing whenever f is decreasing. The third option is h is decreasing whenever f is increasing. The fourth one is h is decreasing whenever f is h is decreasing whenever f is decreasing. So these are the options here. Whenever hx equal to fx minus f square plus f cube. For every real number x, then h is. Now given hx is fx minus f of x whole square plus fx whole cube. H depends on fx. Now differentiating with respect to x. Now h dash x is differentiating fx, we get f dash x. Differentiating fx whole square, we get 2fx into f dash x, of course, by function of function rule, assuming this one has one variable. For x square form, this is x square form, hence 2x into derivative of fx follows, hence f dash x, plus similarly x cube derivative. So this is 3fx whole square into derivative of the base function fx follows, f dash x follows. The derivative of hx is f dash x minus 2fx into f dash x plus 3 into fx whole square into f dash x. This is taking f dash x common here, we get 1 minus 2fx plus 3fx whole square into f dash x. That is h dash x. Now I will write this one as 1 minus 2fx plus fx whole square plus 2 into fx whole square into f dash x. I am splitting 3f square as f square plus 2f square. Based on this, from the first three terms, we can write 1 minus fx or fx minus 1. 1 minus fx whole square from the first three terms plus 2 into fx whole square into f dash x. Just here from the first three terms, you can write it as either fx minus 1 whole square or 1 minus fx whole square. Anyway, this is a perfect square. This is a perfect square, positive. This is clearly positive or non-negative, greater than or equal to 0. This is also greater than or equal to 0. So this total term is greater than or equal to 0. Hence, the monotonic nature of hx depends on only f dash, because this is positive quantity into f dash x. Once f dash is positive, h dash is positive. H dash positive, hx is increasing. Once f dash is negative, this h dash is negative, because it is always positive into negative. Once it is negative, hx is decreasing. So the nature of hx depends on only f dash x. So here once f dash x is positive, then h dash x is positive. That means, therefore, if f dash x is greater than 0 implies h dash x is greater than 0. In such case, hx is increasing when f is increasing. You can conclude that hx is increasing whenever f is increasing. Or if f dash x is negative, that implies h dash x is negative. In such case, hx is decreasing when f is decreasing. So based on f only, either hx is increasing or decreasing. That means whenever f is increasing, correspondingly the hx is also increasing. Whenever f is decreasing, correspondingly h is decreasing. So first one is the right option. H is increasing whenever f is increasing. Again, h is decreasing whenever f is decreasing. Both 1 and 2, multiple options. Both 1 and 2 are the right options here. Both 1 and 2 are right options here. Next one. Next problem. Every invertible function inversible, not invertible function is, the first option is here, certainly monotonic function. That means either increasing or decreasing, of course. That is either increasing or decreasing. Constant function only. identity function, identity function fx equal to x, a straight line which represents a straight line through origin. Fourth one, not necessarily monotonic function, not necessarily monotonic function. This is also one important conceptual question. So such questions may be given in MSET and even JEE mains. Every invertible function is certainly monotonic, not necessarily monotonic. Certainly constant function is an identity function. Invertible function, let f is invertible. Invertible function means that is f inverse exists. F is invertible means f inverse function exists. Let y equal to f inverse x. Let us consider this function be f inverse x. F inverse means, it does not means 1 by fx. 1 by fx is different from f inverse. 1 by fx is the reciprocal function of f, but not inverse function. That should be observed here. So, y equal to inverse function of f. Once y equal to f inverse x means it is 1 1 and on 2. F is 1 1 and on 2. Its f inverse also 1 1 and on 2. So that implies f of y equal to x. By definition of the invertible function, f of y equal to x. Now differentiating with respect to x on both sides. This is, so it is a function of y depends on x. So you can differentiate both sides with respect to x. We get f dash of y into dy by dx follows here equal to 1. Therefore, dy by dx equal to 1 by f dash of y. Here f dash of y cannot be 0. F dash of y cannot be 0 because the denominator cannot be 0. Once it is 0, derivative does not exist. So, f dash y cannot be 0. Once f dash y cannot be 0 means either f dash y is more than 0 or less than 0. So, dy by dx exists. So, dy by dx exists if f dash y exists and not equal to 0. Therefore, f inverse x is monotonic, certainly monotonic, since either f dash y positive or f dash y negative, because it cannot be 0 means either positive or negative. That should be followed. Monotonic function. Moreover, since it is obvious that once the function is invertible, it is continuous and it is 1 1 and on to in its domain. 1 1 and on to in its domain. Suppose the domain of the function is AB, it is 1 1 and on to. That means for each and every x, it has one unique y value, like this. That means either in this form or in this form, the curve must be exist. So either increasing or decreasing, only it is possible. Hence, every invertible function is certainly monotonic, either increasing or decreasing. This is one good conceptual question. One must have knowledge of the 1, 1 on 2 functions and what is the invertible function. Here the denominator cannot be 0. Once it is 0, the derivative does not exist. Once the derivative does not exist, you cannot discuss the nature of the function, monotonic nature of the function. So, derivative exists and equal to 0 only, you can say that the function is constant function. Since f dash lies in the denominator, it cannot be 0. It cannot be constant function. Hence, certainly it must be either more than 0 or less than 0. So, that's why the function is always monotonic in such case. Here another problem. Tan x is greater than x when x lies in the open interval 0 to pi by 2, the open interval pi by 2 to pi, the open interval minus pi by 2 to 0, of course, that means in the fourth quadrant, and this is minus pi by 2 to pi by 2, that means fourth and first quadrants. So this is first quadrant, this is second quadrant, this is fourth quadrant, this is fourth plus first quadrants. This inequality follows in which quadrant? Tan x values are more than x. Now in such case, whenever you have to compare two functions. This is algebraic function, this is trigonometric function. You have to compare these two. To make comparison between these two, let us consider the function. Let f(x) equal to tan x minus x here. Let us consider f(x) equal to tan x minus x. Now f dash x. Taking derivative, its derivative, f dash x, derivative of tan x, that is secant square x minus derivative of tan x is secant square x minus derivative of x is 1. F dash x is secant square x minus 1. We know that 1 plus tan square x is secant square x. So that implies secant square x minus 1 is tan square x. This is already known to you. 1 plus tan square x is secant square x, which is secant square x minus 1 is tan square x. So based on this, f dash x equal to tan square x. For all real values of x, f dash x is tan square x. Since it is a perfect square, it is greater than or equal to 0. It is f dash x is greater than or always greater than or equal to 0. In every interval, f dash x is greater than or equal to 0. So f dash x is greater than or equal to 0 means, therefore, f is an increasing function. An increasing function. I am not saying that it is strictly increasing. F is increasing function for all x. Here the given function tan x minus x is an increasing function for all x. Since it is increasing, by definition of the increasing function, whenever case 1, if x greater than 0, if x greater than 0, then f of x is greater than f of 0, since it is increasing, since f is increasing for all x, f is increasing for all x. So fx is greater than f of 0. So whatever the relation between x1 and x2, the same relation follows between their functional values by definition of the increasing function. So fx is more than f of 0, you can take this. Fx means tan x minus x is greater than, f of 0 means tan 0 minus 0, that gives us clearly 0, hence tan x minus x is greater than 0. So since x is more than 0, x is more than 0, you can say that tan x minus x is greater than 0. Therefore, tan x is greater than x. Tan x is greater than x. When x lies between 0 and pi by 2 only, tan x is more than x. Because in the second quadrant tan is negative, whereas this is positive. A negative quantity cannot be more than the positive quantity. Here x is negative, so it is not possible as per our fx is more than f of 0 for x greater than 0 follows it is not possible, because here x is less than 0. Here is also x takes the negative values, so not possible. These two are not possible. Here tan is negative and x is positive, so here this is also not possible. The one and only the possibility is the first quadrant. So whenever 0 is less than x is less than pi by 2 only, tan x is more than x. And since in the second quadrant tan x is negative, x is positive, a negative quantity cannot be greater than positive quantity. So therefore we can conclude that for 0 is less than x is less than pi by 2 only, tan x is greater than x follows as per our given options. That is follows. If it does not follows, you have to go through the other options also. So other cases, this case. Here I am discussing with one case itself, because in the second quadrant, though x is positive, tan x is negative. A negative quantity cannot be more than positive quantity. So it does not follows in this case. Clearly it is negative and it contains negative values, hence these three does not follows in this case. So the right option is only the first quadrant. So in the first quadrant only tan x is more than x. So such inequalities to be solved or to be evaluated like this. Once you take that function as, you take all the terms from one side of the inequality, take it as fx and find f dash x, and based on f dash x and its sign, either positive or negative, we have to check the monotonic nature of the given function. By applying the definition of the monotonicity of the function, you can conclude the interval in which the inequality is valid. Next one. Fx equal to sin x minus cos x minus ax plus b decreases for all x that belongs to R, then a less than 1. This is possible for a greater than 1, and this is possible a less than root 2, possible for a greater than root 2. This is also one important one. Fx equal to sin x minus cos x minus ax plus b decreases for all x, for all real values of x. Then a follows which inequality? For this, let us consider fx equal to sin x minus cos x minus ax plus b. Fx equal to sin x minus cos x minus ax plus b. So f dash x is derivative of sin x here minus derivative of cos x here minus a into derivative of x and derivative of b itself. So differentiating different functions here, derivative of sin x is with respect to x is cos x, derivative of cos x is minus sin x, so minus of minus sin x, minus a into derivative of x is 1, derivative of constant is 0, hence we get cos x plus sin x minus a. Now this is decreasing, the function is decreasing, f is decreasing, then clearly f dash x is negative, decreasing, f dash x is less than 0. Of course, here I am taking strictly decreasing sense. So f dash x is less than 0 implies cos x plus sin x minus a less than 0, a greater than cos x plus sin x. This is therefore a greater than root 2 into 1 by root 2 cos x plus 1 by root 2 sin x. A greater than root 2 into 1 by root 2 cos x plus 1 by root 2 sin x. Therefore, a greater than root 2 into, it may be written as sine of pi by 4 plus x. I am writing all this function as single trigonometric function. Single trigonometric function, sine of pi by 4 plus x. Sine pi by, since you can write it as sine pi by 4, you can write it as cos pi by 4. Sine of a plus b form, sine a cos b plus cos a sin b form. Hence, a greater than root 2 into sine of pi by 4 plus x. But sine pi by 4 plus x lies between minus 1 and 1, which implies root 2 sine of pi by 4 plus x still lies between minus root 2 and plus root 2. That means this value root 2 sine pi by 4 plus x always lies between minus root 2 and plus root 2, means that value always lies between minus root 2 plus root 2. This value always lies between minus root 2 plus root 2. But whereas a is more than that value. More than that value means more than its maximum value. A is more than its maximum value. The maximum value of this function is root 2. Hence certainly a is more than root 2. Therefore a greater than root 2 follows. So this is possible. This is possible whenever a is more than root 2 only. Once a is more than root 2, f dash x is less than 0. So fourth option is the right option here. A more than root 2 follows. Because f is decreasing, f dash x is less than 0. In such case, a greater than cos x plus sin x, cos x plus sin x. Just I am writing this cos x plus sin x as a single trigonometric function as root 2 into sin of pi by 4 plus x itself. Based on the range of sin value, sin of pi by 4 plus x for all real values of x lies between -1 and 1. Hence, it always lies root 2 sin of pi by 4 plus x lies between minus root 2 and plus root 2. Once this value takes its maximum value root 2 and a is more than that value, means a takes more than root 2 value. A takes more than root 2 value. So, this is the right option in this case. Fx equal to sin x minus cos x minus ax plus b, decreasing for all x that belongs to R. Then a must be greater than root 2. Try to practice such problems which are important to the objective examinations. Next problem. Fx equal to sin inverse of sin x is increasing in. The options are 2n pi minus pi by 2, comma 2n pi plus pi by 2. Where for all n that belongs to z, of course. The second option is 2n pi plus pi by 2, 2n pi plus 3 pi by 2 for all n that belongs to z. The third one is minus pi by 2 to pi by 2. Fourth one is pi by 2 to 3 pi by 2. Fx equal to sin inverse of sin x. Fx equal to sin inverse of sin x is increasing. So here Fx is sin inverse of sin x. Therefore, finding the derivative here. Finding the derivative of sin inverse of sin x. For sin inverse function, the derivative is 1 by root over 1 minus this function square. Sin square x into d by dx of sin x follows. For sin inverse of z, the derivative is 1 by root over 1 minus z square. Here z is a function of sin x, z is a function of x. Hence I am taking the derivative of z with respect to x once again. Derivative of sin x is clearly cos x. Cos x by square root of 1 minus sin square x. Square root of 1 minus sin square x is mod cos x. Mod cos x. This is 1 for cos x is positive, because once cos x is positive, mod cos x is cos x itself. Minus 1 for cos x is negative. F dash x is positive, clearly positive. F dash x is clearly positive whenever cos x is greater than 0. So therefore, f dash x is positive for cos x is greater than 0. That is, cos x is positive in fourth and first quadrants. So that fourth and first quadrant means x belongs to minus pi by 2 to pi by 2. minus pi by 2 to pi by 2. In more generally, generalizing this concept, x belongs to 2n pi minus pi by 2 comma 2n pi plus pi by 2 for n belongs to z only. More generally means once in this case only, in this interval minus pi by 2 to pi by 2 only, cos is positive, hence in such case f dash x greater than 0, f is increasing. F dash x is greater than 0 for cos x greater than 0, then f is increasing. So that is x belongs to minus pi by 2 to pi by 2. More generally, adding 2n pi, the same interval we are taking. So the actual right option is this one. This is only a sub interval of this one, a particular case. This is a particular case. This is the generalized case. Hence the right option is the first option. Consider this one. Of course, this is also an option, but more generalization, this is the right option. Fx equal to log x by x, x being greater than 0, is decreasing in dash interval 0 to e to infinity, 0 to infinity, minus infinity to plus infinity. Fx equal to log x by x, for x being positive, is decreasing. So let us consider fx equal to log x to the base e by x for x greater than 0. Now derivative. F dash x is by u by v rule. This is x square. X into derivative of log x is 1 by x minus log x into derivative of x is 1. Just apply quotient rule. X into 1 by x, derivative of log x is 1 by x, minus log x into derivative of x is 1. X cancel, so 1 minus log x by x square. Now function is f is decreasing, implies and implied. F dash x is less than 0. So the numerator 1 minus log x to the base e less than 0. Since the denominator is positive for all x, the denominator is x square is positive. Since x is positive, x square is also positive. 1 minus log x to the base e less than 0. So that 1 is less than log x to the base e, or that is log x to the base e greater than 1 implies x greater than e power 1, that is e. So whenever this is 0, this is 1, this is 2, this is e, this is 3. E always lies between 2 and 3. Once x greater than e only, the first derivative f dash x is negative. Greater than e means whenever x belongs to, therefore x belongs to e to infinity, then f dash x is negative, hence f is decreasing. So the right option is here, second option, e to infinity.